Imagine having a conversation with a computer that can understand and respond to you in a way that feels almost human like. This is the promise of large language models, a type of artificial intelligence that has revolutionized the field of natural language processing. But have you ever wondered how these models work and what's behind their ability to generate text, answer questions, or even create entire stories? In this video, we'll take a deep dive into the world of large language models, exploring the concepts of deep learning, word embeddings, neural language models, and the transformer architecture that makes it all possible. We'll also discuss the latest advancements in NLP, including instruction fine-tuning, in-context learning, and advanced prompting techniques, as well as the importance of alignment, parameter-efficient fine-tuning, and knowledge graphs. Additionally, we'll examine the challenges of open book question answering, graph retrieval augmentation, and the potential pitfalls of hallucination, bias, and toxicity, and how guardrails and mitigation strategies can help prevent them. So whether you are a beginner or an experienced in the field, this video aims to provide a comprehensive and accessible introduction to the fascinating world of large language models and NLP. So join us onto this journey and discover the exciting possibilities that these technologies have to offer. So let's get started with understanding what is large language models. Basically, large language models are artificial intelligence systems that can understand, generate, and process human language at a large scale. They are trained on vast amounts of text data, which enables them to learn patterns, relationships, and structures of languages. These models can perform various tasks such as language translation, text summarization, sentiment analysis, and text generation. Next comes natural language processing, which is a subfield of artificial intelligence that deals with the interaction between the computers and humans in natural language. It's a multidisciplinary field that combines computer science, linguistics, and cognitive psychology to enable computers to process, understand, and generate human language. Basically, this natural language processing involves tasks such as tokenization, means breaking down text into individual parts or tokens. Parts of speech tagging means identifying the grammatical category of each word, say noun, verb, adjective. Next, named entity recognition means identifying named entities such as people, organization, and location. Sentiment analysis means determining the emotional tone or sentiment of the text. Next comes the deep learning, which is a subfield of machine learning that involves the use of artificial neural networks to analyze and interpret data. These networks are composed of multiple layers of interconnected nodes, that is neurons, that process and transform inputs into meaningful representation. Deep learning is particularly useful for NLP tasks because it can learn complex patterns and relationships in the language models. Next comes the word embeddings. So word embeddings are a way to represent words as vectors in high dimensional space. This allows words with similar meanings to be closer together in the vector space. And there are two popular word embeddings techniques. First is word-to-vec, which uses neural networks to learn word embeddings from large amount of text data. It has two architectures, continuous bag of words and skipgram. Next comes the GLOW, which uses a matrix vectorization technique to learn word embeddings from co-occurrence matrices of words. Basically, these word embeddings have several benefits, including capturing semantic relations, that is, words with the similar meanings are closer together in the vector space. Reducing dimensionality means word embeddings can reduce the dimensionality of text data, making it easier to process. And finally, this word embeddings can improve the performance of natural language processing models by providing a more meaningful representation of words. Next comes neural language models. They are a type of deep learning model designed specifically for NLP tasks. They can be used for tasks such as language modeling, text generation, and machine translation. And there are different types of neural language models like convolutional neural networks, which uses convolutional and pooling layers to extract local features from text data. Recurrent neural network uses recurrent connections to model sequential dependencies in text data. Long short-term memory is a type of recurrent neural network that uses memory cells to learn long-term dependencies. Sequence-to-sequence models uses encoder-decoder architecture to model sequential dependencies in text data. And finally, attention mechanism allows the model to focus on specific parts of input data when generating the output. Next comes sequence to sequence models, which consist of an encoder and decoder. Here, encoder takes in a sequence of words and outputs a fixed length vector representation. Decoder takes this vector representation and generates a sequence of words. Basically, these sequence to sequence models are used for tasks such as machine translation, text summarization, and chatbots. Next comes the attention mechanism. So basically, this attention mechanism are used in sequence to sequence models to allow the model to focus on specific parts of input data when generating output. And this is particularly useful for tasks such as machine translation, where the model needs to attend to specific words or phrases in the input sentence to generate the correct translation. Now, the transformer is a type of neural network architecture introduced in 2017, specifically designed for sequence to sequence tasks such as machine translation, text summarization, and chatbots. Here, this transformer architecture is based on self-attention mechanism, which allow the model to weigh the importance of different input elements such as words or tokens when generating output. And this is different from the traditional recurrent neural network, which uses recurrent connections to model the sequential dependencies. Now, this transformer architecture consists of an encoder, which takes in a sequence of tokens such as words or characters and outputs a sequence of vectors. Decoder takes the output vectors from the encoder and generates a sequence of tokens. Next comes the positional encoding. Now, in the transformer architecture, the input sequence is encoded using a technique called positional encoding. This is necessary because the transformer architecture is permutation invariant, meaning it does not inherently capture the order of input sequence. So, positional encoding adds information about the position of each token in the sequence, allowing the model to capture sequential dependencies. And there are several types of positional encoding, like absolute positional encoding, which uses a fixed encoding for each position in the sequence. Relative positional encoding uses relative encoding that depends on the distance between tokens. Next, the tokenization. So tokenization is the process of breaking down text into individual tokens such as words or characters. And these are some tokenization strategies, which includes word level tokenization, means breaking down text into individual words. Subword level tokenization means breaking down text into subwords, which are smaller units of text that can be combined to form words. Character level tokenization means breaking down text into individual characters. And some popular tokenization strategies includes word piece, which is a subword level tokenization strategy that uses the combination of word and subword tokens. Byte pair encoding is a subword level tokenization strategy that uses a combination of word and subword token. Next comes the language models. So first is a decoder only language model, which is a type of language model that uses only the decoder component of transformer architecture. This type of model is trained on the sequence of tokens and generates a sequence of tokens as output. Now, decoder-only language models are used for tasks such as text generation, language translation, and chatbots. Next, prefix language model is a type of language model that uses the prefix of input sequence to generate the rest of the sequence. And this type of model is trained on the sequence of tokens and generates a sequence of tokens as output, but only uses the prefix of input sequence to generate the output. Next, the decoding strategies, which are used to generate output from the language model. And there are several decoding strategies like greedy decoding, which selects the most likely token at each step. Beam search decoding selects the most likely sequence of tokens by exploring multiple possible sequences. Sampling decoding selects a token randomly from the probability distribution. Now, encoder-only language models is a type of language model that uses only the encoder component of transformer architecture. This type of model is trained on the sequence of tokens and outputs a fixed length vector representation. Encoder-only language models are used for tasks such as text classification, sentiment analysis, and information retrieval. Now, encoder-decoder language model is a type of language model that uses both the encoder and decoder component of transformer architecture. This type of model is trained on the sequence of tokens and generates a sequence of tokens as output. Encoder-decoder language models are used for tasks such as machine translation, text summarization, and chatbots. And some common encoder-decoder language models includes BERT, which uses a multi-layer bidirectional transformer encoder to generate contextualized representation of words in the input sequence. Roberta uses modified version of BERT architecture with a different optimizer and training procedure. Next comes instruction fine-tuning, which is a technique used to adapt a pre-trained language model to follow specific instructions or tasks. The goal is to fine-tune the model to understand the instructions and generate responses that are relevant and accurate. And the process involves pre-training means training a large language model on vast amount of text data, fine-tuning the pre-trained model on smaller data set of instructions and corresponding responses, and finally evaluating the fine-tuned model on the test set to measure its performance. Instruction fine-tuning is useful for tasks such as classifying text into categories based on instructions, analyzing the sentiment of text based on instructions, and finally answering questions based on instructions. Now, in-context learning is a technique used to adapt a pre-trained language model to learn from few examples or context. Here, the goal is to enable the model to learn from small amount of data and generate accurate responses. The process involves training a large language model on vast amount of text data. Then in-context learning means providing the model with few examples or context and fine-tuning it to learn from data. And finally, evaluating the model on test set to measure its performance. In-context learning is useful for tasks such as learning from few examples. Zero-shot learning means learning without any examples. And meta-learning means learning to learn from few examples. Next comes advanced prompting, which is a technique used to improve the performance of language models by providing them with more informative and structured prompts. Here, the goal is to enable the model to generate more accurate and relevant responses. Some advanced prompt techniques include chain of thoughts, which provide the model with sequence of prompts that are related to each other. Graph of prompts or the graph of thoughts provide the model with a graph of prompts that are related to each other. Prompt chaining means providing the model with a sequence of prompts that are related to each other, where each prompt is generated based on previous prompts. And advanced prompting is useful for tasks such as text generation, means generating text based on prompts or answering questions based on prompts, and finally generating dialogue based on prompt. Next comes alignment, which refers to the process of ensuring that the language model's output is aligned with the desired output or task. Here, the goal is to ensure that the model generates responses that are relevant and accurate. Alignment can be achieved through aligning the training data with desired output or task, then aligning the language model with the desired output or task in the model alignment, or prompt alignment means aligning the prompt with a desired output or task. Alignment is useful for tasks such as classifying text into categories, analyzing the sentiment of text, or answering questions. Next comes parameter efficient fine-tuning, which is a technique used to fine-tune a pre-trained language model while minimizing the number of parameters that needs to be updated. Here, the goal is to reduce the computational cost and memory requirements of fine-tuning. Parameter efficient fine-tuning involves freezing some of the model's parameters and only updating a subset of them, or adding adapters to the model to enable fine-tuning of specific parameters, then updating the model's parameter using low-rank metrics. Parameter efficient fine-tuning is useful for tasks such as domain adaptation, means adapting a pre-trained model to a new domain. Task adaptation means adapting a pre-trained model to new task. Efficient fine-tuning means pre-training a fine-tuned model while minimizing computational cost and memory requirement. And some popular parameter efficient fine-tuning includes adapter-based fine-tuning, means using adapters to fine-tune the model, or using low-rank matrices to fine-tune the model, and finally using bit-level fine-tuning to update the model's parameter. Next comes the knowledge graphs, which is a type of database that stores information in the form of graph, where entities such as people, places, and things are represented as nodes and relations between them are represented as edges. Here the goal is to provide the structured and organized way of representing knowledge, making it easier to search, query, and reason about the data. A knowledge graph typically consists of entities, that is the nodes that represent people, place, things, and concepts. Relationships are the edges that connect entities and represent relations between them. Properties are the attributes or characteristics of entities such as names, description, and categories. Now, knowledge graphs are useful for tasks such as answering questions by traversing the graph and finding relevant information. Entity disambiguation means identifying the correct entity based on context and relationship. Recommendation system is recommending entities based on relationship and properties. Next comes open book question answering, which is a type of question answering task where the model has access to the large corpus of text or knowledge graph and can use this information to answer questions. Here the goal is to evaluate the model's ability to retrieve and use relevant information from the corpus or graph to answer questions. Basically, this open book question answering involves analyzing the questions to identify relevant entities, relationships, and context. Information retrieval means retrieving relevant information from corpus or graph, and finally generating an answer based on that retrieved information. Open book question answering is useful for tasks such as factoid question answering, means answering questions that require retrieving specific facts or informations. Open-ended question answering means answering questions that require generating a longer response or explanation. Conversational question answering means answering questions in a conversational setting where the model needs to understand context and follow-up questions. Next comes the graph retrieval augmentation, which is a technique used to improve the performance of graph-based models such as knowledge graph by augmenting the graph with additional information or edges. Here the goal is to enhance the graph's ability to represent relationship and entities, making it more effective for tasks such as question answering and entity disambiguation. Graph retrieval augmentation involves graph expansion, means adding new nodes and edges to the graph based on external information or knowledge. Graph densification means adding new edges between existing nodes to increase the graph's connectivity. Graph pruning means removing unnecessary nodes and edges to reduce noise and improve graph quality. Graph retrieval augmentation is useful for tasks such as knowledge graph completion, means completing missing information in the graph. Entity recognition means identifying and disambiguating entities in the graph. Question answering means answering questions by traversing the augmented graph. Some popular graph retrieval augmentation techniques include graph attention networks, which means using attention mechanism to weight edges and nodes in the graph. Graph convolutional networks use convolutional neural networks to learn graph representation. And finally, this graph autoencoder uses autoencoders to learn compact graph representation. And these are some additional details on this techniques mentioned. First is the graph attention network, which is a type of neural network designed for graph structured data. They use attention mechanism to weight edges and nodes in the graph, allowing the model to focus on relevant information. Graph convolutional networks are a type of neural network designed for graph structured data. They use convolutional layers to learn graph representation, allowing the model to capture local and global patterns in the graph. Graph autoencoders are a type of neural network designed for graph structured data. They use autoencoders to learn compact graph representation, allowing the model to capture essential information and relationships in the graph. And these techniques can be used for a variety of tasks, including question answering, entity recognition, and graph completion. They can also be used in combination with other techniques such as knowledge graph embedding and graph retrieval augmentation to improve the performance of graph-based models. Next comes the overview of recently popular models. So in nowadays, several models have gained popularity. Some common models are BERT, which is a language model developed by Google that uses multi-layer bidirectional transformer encoder to generate contextualized representation of words in input text. Roberta is a variant of BERT that uses the different optimizer and training procedure to improve the model's performance. Transformers is a type of neural network architecture that uses self-attention mechanism to model relationship between the input elements. GAN is a type of deep learning model that uses generator and discriminator to generate new data samples that are similar to training data. And these models are widely used for tasks such as classifying text into categories such as spam versus non-spam email, analyzing the sentiment of text such as determining whether the review is positive or negative, or answering questions based on the given text or context, and finally generating text based on given prompt or topic. Next comes hallucination, which refers to the phenomena where the model generates text or output that is not based on actual input or context. And this can happen when a model is overconfident or when it is not properly trained or fine-tuned. Hallucination can be a problem in various NLP tasks such as generating text that is not based on any actual input or context, or providing answers that are not based on any actual information or context, and finally generating summaries that are not accurate or relevant to the original text. Next comes the bias, which refers to the phenomena where the model is unfair or discriminatory towards certain groups or individuals. This can happen when model is trained on biased data, or when it is not properly designed or fine-tuned. Bias can be a problem in various natural language processing tasks such as classifying text in a way that is unfair or discriminatory towards certain groups or individuals, or analyzing sentiment in a way that is biased towards certain group or individuals, and finally providing answers that are biased or unfair towards certain groups or individuals. Next comes toxicity, which refers to the phenomena where model generates text or output that is harmful, offensive, or inappropriate. This can happen when the model is not properly designed or fine-tuned, or when it is trained on toxic data. Toxicity can be a problem in various natural language processing tasks such as generating text that is harmful, offensive, or inappropriate, providing answers that are harmful, offensive, or inappropriate, and finally generating responses which are offensive or inappropriate. Next, guardrails, which refers to the techniques and strategies used to prevent or mitigate the problems of hallucination, bias, and toxicity in the natural language processing models. Some common guardrails includes data quality control, which ensures that training data is highly qualified, diverse, and representative of the target population. Model evaluation means evaluating the model's performance on a variety of metrics including accuracy, fairness, toxicity, or having human evaluators review and assess the model's output to ensure that it is accurate, fair, and safe. And finally, regular auditing the model's performance and output to ensure that it is not hallucinating, biased, or toxic. Next, mitigation refers to the techniques and strategies used to reduce or eliminate the problems of hallucination, bias, and toxicity in natural language processing models. Some mitigation strategies includes augmenting the training data with additional examples or scenarios to improve the model's robustness and fairness. Model regularization means regularizing the model's parameters to prevent overfitting and improve its generalizability. Ensemble methods means combining the predictions of multiple models to improve the overall performance and robustness. Human oversight means having human overseas review and access the model's input to ensure that it is accurate, fair, and safe. And that's the wrap. Our journey through the world of large language models and natural language processing has taken us on a fascinating tour of the latest advancements in artificial intelligence. From the fundamentals of deep learning and word embeddings to the cutting-edge techniques of instruction fine-tuning and advanced prompting, we have explored the many ways in which these models are revolutionizing the way we interact with language. We have also examined the challenges and pitfalls that come with these technologies, including hallucination, bias, and toxicity, and discussed the importance of guardrails and mitigation strategies, ensuring that their safe and responsible deployment. As we look to the future, it's clear that large language models and natural language processing will continue to play an increasingly important role in shaping the world around us, from virtual assistant and chatbots to language translation and text generation. Whether you are a researcher, developer, simply someone interested in the possibilities of AI, we hope that this video has provided a comprehensive and accessible introduction to the existing world of large language models and natural language processing and we look forward to seeing the many innovative applications and the breakthroughs that these technologies will enable in the time to come. Thank you.